Consider a curve in R3 that has a path. A path is a mathematical function that gives you a vector locating each point on the curve. Now, what we're going to do here is define some new vectors that are relative to points on C. These vectors are going to help us understand geometric properties of the curve, and they're also going to help us understand properties of motion when following the path along the curve. Now, recall that we've talked about the unit tangent vector. Now, the unit tangent vector is going to be denoted by capital T of t, and all it is the derivative of the vector function r of t and divides it by its length. Now, remember that the r prime of t vector is always tangent to the curve, and it's tangent at the point that's given to you by r of t. So if I take a look at this picture here, there's some tangent vector r prime of t. Now, generally, we don't know what the length of that vector is. It may or may not be unit length. We define a scaled version of this vector that has a length of 1. So the unit tangent vector is just a scaled version of that derivative vector. If we wanted to take the length of this unit tangent vector, we would be taking the length of this r prime vector divided by its own length. Well, remember, this is a scalar, and because it's a scalar, it can be brought out of the length of the vector. This is just a property of lengths. The length of the unit tangent vector is 1. Because of that fact, if I were to square it, I would get 1 again. And remember that the length of a vector squared is simply the vector dotted with itself. We are going to take the derivative of both sides of this expression, remembering that the derivative of 1 is a 0, and using the product rule on this side, what we will find is that we'll get 2t dotted with its derivative. Now, of course, we're making an assumption about the path here. We are assuming that t prime exists, and that means we need an additional derivative of the derivative. T and t prime are orthogonal to each other. And that's going to lead us to defining a new unit vector. And this new unit vector is called the unit normal vector. And we will define it as capital N of t vector, t prime of t, divided by the length of t prime. Now remember, the unit vector t has a length of 1, but when we take its derivative, we don't have any idea about what the new length will be. So that's why we will scale this so that it does have a length of 1. Scaling a vector doesn't destroy orthogonalities. If two vectors are orthogonal, making one longer or shorter doesn't kill the orthogonality. You could think of this as some constant times this vector t prime, if you'd like. And if I already know that t dotted with t prime is equal to 0, 1 over that constant times n, and that still give me 0 because I can take this out by dot product properties, and then as before, I will find. So I've defined a couple of different vectors here. What does it mean to have these? Each of these vectors is a function of this parameter t. So these vectors change depending on location or depending on the point on your particular curve. And I'm going to draw a curve again here just to try to illustrate to you what's happening. As before, if we have a point on the curve, so there's r of t, the unit tangent vector is tangent to the curve. It can change its direction. So for example, if I were to pick a different location on the curve, the tangent vector points in a different direction. This hopefully explains why it needs to be a function. We've already discussed that the unit normal vector is orthogonal to t, but which way should it point? N always points in the direction in which t will change. If I were to take this first point given on the curve, I would see that the tangent vector would slowly start to turn downward. That means the unit normal vector will be pointing in that direction, toward the direction of change of the tangent vector. If I were up here, the unit tangent vector wants to start curving upward. And that means that the unit normal vector at this point wants to point upward, toward that direction of change. So let's take a look at an example. I'm going to consider a helix that's in the positive y direction. Now remember that a helix is essentially a curve that wraps itself around a cylinder. So you could imagine that I have a cylinder pointing in the positive y direction, and then a helix wraps itself around according to the right-hand rule. I would wrap around, go behind it, and then wrap around again, and go behind, etc. So this is a picture of the helix. Now in this particular case, the curve is parameterized by this function, 2 pi t in the I, tj, and then cosine of 2 pi t in the k direction. So what I would like to do is calculate the unit normal and the unit tangent vector. I need to calculate the derivative, so I will use the chain rule, and I'll get a 2 pi cosine of 2 pi t I plus 1j minus 2 pi sine of 2 pi t in the k direction. The length of this vector, 4 pi squared cosine squared of that quantity, plus 1 squared plus another 4 pi squared sine squared of that quantity. And then I need to take the root of all of it. This is going to give me a 1 plus a 4 pi squared cos squared and sine squared. I know that that equals 1. So at the end of the day, I will get a 1 plus 4 pi squared. This allows me to calculate the unit tangent vector. It will be 1 over the length of the derivative vector times the derivative vector. So I'll get a 2 pi cos 2 pi t in the I direction, a j, and then a minus 2 pi sine 2 pi t in the k direction. So what this does is it provides us with a vector that changes depending on where it is in the curve. So if I just scroll back up to the picture, at any point, there's a position vector. So I'm not going to draw in the position vector because it will clutter up the diagram. The unit tangent vector pointing this way. At this particular location, there's the unit tangent vector. At this particular location, there's the unit tangent vector. So as expected, the unit tangent vector changes its orientation depending on where I am on the curve. To calculate the unit normal vector, I need the derivative of the unit tangent vector. So there's going to be a constant factor of 1 plus 4 pi squared here. I need to use the chain rule again. I will get a 4 pi squared with a negative sine of 2 pi t in the I direction. I will get no contribution from the j direction, and then I will get another negative 4 pi squared cos 2 pi of t in the k direction. So there are only two components to this vector. The length of this vector, the square root of all of these terms squared. So 4 pi squared over the square root of 1 plus 4 pi squared. That's going to be squared because it appears in every component. And then I will get a sine squared of 2 pi t plus a cosine squared of 2 pi t. As always, this is 1. All of these terms are in the square root. So because of the square root and the square property, I'm going to get 1 plus 4 pi squared and a 4 pi up top. 4 pi squared up top. Now note, this is not equal to 1. So this is not a unit vector. So you have to be careful. Just because t might be a unit vector, its derivative is not going to be a unit vector in general. The unit normal vector is simply the ratio of that unit tangent vector derivative, ends up being a little messy, times the t prime vector. Well, the t prime vector everything had a factor of 4 pi squared, and it was sine of 2 pi t I plus cosine of 2 pi t j. And there was also the root term here that I've forgotten. Well, what conveniently happens is that the 4 pi's go away, these roots go away, and what you're left with is something very simple. Negative sine of 2 pi t I plus cosine of 2 pi t j. Now, it's clear from this that the length of this unit normal is 1. If you just square both components, add them up, you get a 1 and take its root. And because of this negative sign, this thing essentially points inward, similar to circular motion. Now I'm going to scroll back up to this picture, and remember, at any point, the unit normal, it's always orthogonal to the tangent vector, and it always points in toward the curve in this particular example. So what these two vectors do is they provide a moving set of orthogonal vectors. Now finally, we can define a third orthogonal vector. And it's very straightforward to do using the cross product. We are going to define this vector B, binormal vector. It's simply just going to be the cross product of t with n. This is called the unit binormal vector. And the reason I'm allowed to call it the unit is because if I just think about the length of this vector, it's the length of this cross product. Well, from that geometric definition of the cross product, I know that the angle between these two vectors is pi over 2, so this gives me a 1. I know that each of these is a unit vector, and that tells me that the length of this vector is also 1. These three vectors, t and b, they have a local three-dimensional coordinate system at each point on your curve. So you will always have a tangent direction to the curve. The unit normal will always point in the direction of changing tangent. And then finally, this binormal vector is found by the right-hand rule. Each of these vectors follows like so. As you move along the curve, the tangent vector changes, the unit normal vector changes. Consequently, the binormal vector changes as well. They're always mutually perpendicular to each other. So in the example of the helix, we are going to calculate this binormal vector. It'll simply be a cross product of these two. We are going to set up the components of our t vector. The first component gave me a 2 pi cosine of 2 pi t. The second component was just 1 over that square root. And then the third component had 1 over that square root with a negative 2 pi sine of 2 pi t. So definitely the unit tangent vector was messy looking, but the unit normal vector was much more straightforward. I had a negative sine of 2 pi t, a 0, and a negative cosine of 2 pi t. Compute the cross product like normal. The negative cosine of 2 pi t over that square root in the I component. In the j component, cosines that will square together and sines that will square together. Each of these is going to have a negative with that same square root in the bottom. And then finally, your k component, you'll have a negative subtract a negative sine 2 pi of t over that square root. So it's just computational, but at the end of the day, what you will find is that the binormal vector is cosine of 2 pi t over that square root in the I direction, 2 pi over that square root in the j direction, and then you'll have a sine 2 pi t over that square root in the k direction. Now, don't memorize these formulas. What's important is that you're able to calculate them. These three vectors, t and b, they are called a Frenet frame, and you can think of it as a moving coordinate system. They will be helpful in describing geometric and also physical properties of curves and paths.